So welcome to Origin Seminar for February 24th. Thank you everyone for coming. Just quickly before we start, I do want to say that there will be a hard cutoff of 12:50 today, so 10 minutes to the hour, because Chris has to teach at 1 and we don't want to make him late for his own class. So today's speaker is Chris Walker. Hopefully many of you know him or know of him already. Professor of Astronomy at the University of Arizona, who will be speaking to us about GUSTO and the future of far infrared astronomy.
Okay, yeah, thanks, Allison. So Allison's actually helped me teach Astronomy 300B this semester. So we both have to be somewhere. That's right. That's right. So anyhow, I appreciate that very much, Allison. Oh yeah, so thanks for asking me to give a talk today, and I thought it would be timely to discuss the GUSTO project and also what can come after GUSTO in terms of far infrared astronomy. So the first part of the talk, I'll talk about GUSTO, and then the last third or 40%, I'll talk about some future projects that we're all working on going forward. So this is my standard opening slides on these talks. So we live in a galaxy comprised of stars, planets, and people. Where do we all come from? This is actually a picture taken from the site testing on Mount Graham back in the late 80s by Doug Officer, who did the site testing up there at that time. So this is the galaxy, our Milky Way, seen edge on. We can see the dust clouds in there. It's where the stars are made. It's the ISM that we all come from. In the distance, you can see Tucson, Phoenix on the horizon. So it's also kind of an astrobiology slide. So it serves many purposes. So where do we come from? That's the big origins questions. We come from the ISM, gas and dust between the stars, which Alice and I are talking about in 300B this semester. Never get tired of it. One thing we're trying to address with GUSTO is the life cycle of the interstellar medium, which you all are familiar with, I'm sure. Starting with, you can start anywhere, it's a life cycle, but from warm neutral and ionized gas, formation of H1 clouds, formation of molecular clouds, as things continue to contract and get denser and colder, and the contraction continues as long as the cloud can radiate away the heat that it builds up as it collapses. It stays optically thin, but at some point the little cores will become optically thick to their own radiation. That's when you start the protostellar phase of evolution and the evolution of stars. The high mass stars, which drive this life cycle, they never leave the cloud. They never get away. So as they evolve, they can disrupt the cloud through jets and ultimately supernova from explosions or ionization fronts, and you go back again. And so this life cycle can be probed using different atoms and molecules. The ones that we had for GUSTO are shown in gold dashed lines here. This particular plot was made by Craig Colesso a very long time ago, but it serves us well. As you can see, the atom that shows up mostly is ionized carbon. What I'll say is this sort of the diagnostic thread on which the whole life cycle is drawn. These are like little pearls, and it's the C2 is what binds it all together. The reason why is C2 carbon is very abundant. It's like the third thing the star makes: hydrogen, helium, oxygen, carbon, and it blows it out to the interstellar medium through supernova explosions and various things. And also the ionization potential of carbon is below that of hydrogen, which means that while the hydrogen atoms suck up the UV photons pretty much everywhere else, C2 gets its own little lower energy UV photons and allows it to be ionized. And it can be easily excited by collisions with electrons in the ISM, which are photo-dissociated from dust grains. So that's how it all kind of works. So that's why, and also the ionized carbon is the brightest line in the far infrared. It can be up to like 1% of the overall flux of the far infrared in that one line. And this is true not just in a modern galaxy like the Milky Way, but through all cosmic time. So by studying the life cycle of the ISM, and in particular ionized carbon, in our Milky Way, we can use the same ideas and approach to probe the life cycle of the ISM and even primordial galaxies. Okay, and so this is how GUSTO worked. Here's it still exists, it's sitting on the ice. I'll show you a telescopic view from orbit of it out there. Here it is. I'll show the other pictures of it here in a minute. It's a balloon-borne payload. Looks kind of like a satellite, except it has a string here that's hanging from a big old balloon up here. The balloon is bigger than the football field. That's 34 cubic million feet of helium gas. The payload itself weighs about 2 tons. I'll show you pictures of it in reality here in a minute. But this was one of the early slides we made to sell the idea to headquarters. So I've shown this slide since for over 10 years. Doesn't get old. So what we do is we have a little telescope here. It's a 0.9 meter telescope. It doesn't have to be big because what we want to do is an unbiased survey of the galactic plane. Not just look at the hot spots in the galactic plane. We do, but get everything, the spots, everything in between, because we want to understand the whole life cycle. So both the dense cold material and the hot optically thin material. We want to get it all. So as we look along any line of sight, we get a spectrum. The type of detectors we fly are heterodyne receivers, which is just a fancy word for the standard radio technology that you all carry around in your pockets right now or sitting in front of you on a cell phone. So basically we have at every line of sight, we get a spectrum. And that's what's shown down here, of course. That's, as I'll explain in class, it's frequency on the x-axis and loudness on the y-axis. And as you tune across your high frequency radio, you can pick up these various lines of carbon and oxygen and stuff like that. Oh, I forgot to say, the frequencies we're looking at are really high. They're 1.9 terahertz for ionized carbon and 1.4 terahertz for ionized nitrogen. And terahertz is 1,000,000 megahertz, obviously. Okay. All right. So as we tune our radios, normally at rest, the ionized carbon will show up at one frequency, 158 microns, 1.9 terahertz. We speak wave. If you come from the infrared, you speak in wavelength. You come from the radio, usually it's more comfortable with frequency. And of course, frequency rules because frequency is independent of the medium through which the photon travels. So it really should always be frequency. But anyhow, we'll dumb it down and put it in wavelength so everyone can grasp it. Wavelength is something much more physical that people can get. But anyhow, you can see that there isn't just one ionized carbon line. This is as shown here. There's families of them. And what that is due to is that as we go through any one line of sight, we poke through various spiral arms in the galaxy. So each of these represents poking through a spiral arm in the various cloud components within that arm. You can also pick up inter-arm material as well. And so they're spread out, of course, because the galaxy is differentially rotating faster on the inside, getting a little bit slower as you go out. So that spreads the lines out from one frequency to a bunch of them. So what that means is that if you map the whole galaxy, as much of it as you can, if you know the rotation curve of the galaxy, you get a three-dimensional map of what the Milky Way is doing, which I'll show you some preliminary ones just a bit here. As we observed, we did, this is the galactic plane again, in the optical, we did these little meandering scans, and we did, you can think of in the infrared as drift scans, or radio, we call on-the-fly mapping. We're constantly taking data as we go through here, so we don't try to miss anything. So it's fully sampled. This is the region that we're shooting for with Gusto. And then what happens is every 8 to 12 hours, we'll flip the gondola around and go look at the LMC, which is more characteristic of a primordial galaxy because it's low metallicity galaxy, whereas our Milky Way is a relatively high metallicity galaxy. So we also did observations of the LMC, and I'll show you a sample of that in a minute. So by studying the LMC, primordial low mass kind of a galaxy, and the Milky Way, we kind of have the bookends to how the interstellar medium would evolve over cosmic time. All right, fun stuff now. All right, so here's a little video that was put together by Jose Silva, who was a postdoc from ESRON, who was on the trip. ESRON actually provided the detector arrays we used. This was a very multidisciplinary, multi-institutional project. So ESRON built the detector arrays, the Applied Physics Lab built the gondola and the cameras and pointing system. We built the main telescope itself and put everything together and made it work on the elevation axis. It was a big team effort. We had, institutionally, we had on the science team, we had the big hitters. We had Thielens and Hollenbach on our science team. Paul Goldsmith, Gary Melnick, a whole bunch of stars on the team. And they're still heavily involved because now we're at the point where we're gonna actually start analyzing the data that came from it. I should just show you the pretty movie here. So this is Gusto arriving on the ice in Antarctica. It got its own private plane, a NASA C-130, and it shows you it coming out the back of the plane. It's all in this container. It was different in that since it was a big boy explorer type mission, we kept it all together before shipping it. Normally a balloon project, you build it, you test it up north, and then you break it down to like 24 wooden crates and reassemble it on the ice. Here we put it all together and convinced NASA, let's take it down as one integrated unit, except for the solar panels. So here we see it in Hangar 2 or Payload 2 of Antarctica. It's coming out of this box. And instrument people on the line will appreciate this. Other people are sipping their coffee. But it's kind of fun. So it's going to be set up and then put down. So the ride down here on the C-130 was manned by Brian Duffy and Abe Young from our team. They made sure we got here in one piece. Got there in one piece. These are crew that you see wandering around. A lot of the hard hats are from NASA. They're the Columbia Science Facility guys, who are the riggers, they call them, down there, doing all the moving, putting things together, and getting the balloon ready to launch. This is the giant reaction wheel on top for azimuth control, right? Because we don't have the ground to push off of. It's like a 70-pound thing that spins. If you look closely, there's also a bicycle wheel here, literally a bicycle wheel. And that's to take out the pendulation that we might have flying. Our pointing accuracy, our beams are like 45 arc seconds on the sky, diffractional bit of beams, because we're a survey mission. So our pointing accuracy was better than 15 arc seconds. We were able to easily achieve that. And we also have star cameras, which I'll show again in a minute. Oh, here they are. Look like bazookas on the side of the telescope. And then here's what it looks like all together on launch day with the solar panels. Each solar panel can chug out about a kilowatt power. So we have the 2 kilowatts of power available. Payload actually took about 1,100 watts altogether. The payload has a liquid helium door for cooling the detectors, which are superconductors. It held 150 liters of liquid helium. We also augmented that cooling capacity with closed cycle refrigerators from SunPower Cryogenics. This thing up here, we call it the diving board. That's actually a radiator, just like in your car with copper tubes running around. Because the cryo coolers and the local oscillators we used on the heterodyne receivers, in particular, generate a lot of heat. Once you get up to balloon altitude, the ambient pressure is like below 5 millibars. And so you need to get rid of the heat. You can't assume convection is going to take it away. So you have to radiate it into cold space. And so this is like a space type of radiator to shoot it out into space. Otherwise, you'll end up cooking your payload. On the early, we had two progenitor balloon missions called STO-1 and STO-2. And STO-1, we didn't appreciate the fact that you could cook your instrument. And we kept watching the temperatures. One of our amplifiers was almost at the melting point of solder. But luckily it didn't like disintegrate and float around, but it made it. So we learned. So we had an active cooling loop on this baby. Okay, and here is the launch sequence. So here's the payload hanging from a little crane. At the top are like a little pincher claws that hold it. This is the balloon being released. The balloon is choked off right here when it's near the ground to keep the helium up here. Once it gets a little higher, this collar is released, and the balloon actually extends all the way down to the top of this parachute. And then this is like explosive bolts here that when you're done, you can separate the balloon from the parachute. And it just automatically opens up, just like when you're a kid, you may have made like a parachute with a handkerchief and throw in a stone or something. Same kind of deal here. And so we had to set up so that we're downwind. So once the balloon gets up, the wind picks it up, slowly brings it over the top. On this particular day, there was almost no wind, which sounds good, but it's bad in terms of laying out your balloon. So we weren't sure where to put the balloon down, when we could release or not. And in the end, the guy named Core had to gun it. So you can see he's got like wheelies here, trying to get this thing out. The other thing is, it's really a family down there. Between all the groups, we eat and sleep, not sleep together. We all are in the same dormitories. We see each other. We work all hours, and so it's like a big family of like 50 people to make all this stuff happen when it's on the ice. You see it lifting away. Okay, and this is the command center, not the command center, the Science Operations Center. It was over at the ARB, and there's Craig. There he is. He's kind of a little wisp there. He's not. I took this picture. Craig wasn't there, but he was there for about how long were you up? 50, 54, 57 days. He was pretty much in that chair the entire time, making this thing work. We had people here helping out, but mostly Craig. We also had a mission operations center called the MOC at the Applied Physics Lab. So at any given time, there was at least one person at the Applied Physics Lab, one person, mostly Craig here at the U of A, and also another guy down in Palestine, Texas, where the data came down from satellites. Oh yeah, I should also point out that on our mission, we actually got most of our science data, not through TDRs, not through Iridium, which is the standard satellites, but through Starlink, it turned out. Starlink was the most robust thing, so that's what we used almost the entire time. Okay, so what the heck did we do up there? So here's a picture of the galactic plane again, like on summit of Mount Graham. So it looks like a band across the sky. This is the southern part. The galactic center is here. This is IRAS 100 micron map. If I was in class, I would say, how many people heard of IRAS? No one would raise their hand. But it was a big deal back in the early 80s, and it still is a big deal, the data set. So this is looking at the dust emission, the galactic plane. There's 2264, one of my favorite clouds there, and there's others. This little map right here is of a star forming region right there called G333.6. That's the galactic longitude, and that's the galactic latitude. So it's just a little bit below the galactic plane, most of it. And these are the little C2 spectra that Gusto took. This is a position switch map, which means we're at this point, we weren't doing on the fly. We're just trying to figure out, is this thing working? So we look on the target, off the target, subtract the two signals, and the little C2 spectra would pop up. So we made this little mosaic just to make sure we were on target and that the instrument was working correctly. In the end, we actually mapped all this region of the galaxy. We got from what's this, around -30 all the way to +2. So we did get through the galactic plane, through the galactic center. That's what the GEC stands for. You can see how the mission was designed to follow the dust. Where there's dust, there's 100 times more gas, right? In general. Also, here's a chunk of the Large Magellanic Cloud we're also able to map. So it's about 62 square degrees for the galactic plane, a couple square degrees of this. Total number of lines of sight, well over 1 million. Millions of spectra we got in C2 and N2, which is pretty cool. Pretty happy that worked out the way it did. Okay, so here's the eye chart picture for you. So this is one little region. This is this little guy right here toward this star forming region. It has, well, I'm trying to think of the name of it. I'm blanking out here. Let's see. This is while I try to remember the name of it. 3603, sorry, it's NGC 3603. And this was a dust map that was made as a composite image from Sophia and Herschel data. Again, this is the dust, which is pretty, but you got like, it's two-dimensional map, right? You get temperature, column densities. You can look at, by looking at the slope of the Rayleigh Jeans part, you can estimate whether it's carbon or silicon atoms, mostly making up the dust grains. That's pretty much it. Here's a comparable image in C2. So I drew a gold box. And look at this. Look at this. It looks kind of like butterfly wings a little bit. And if you squint here, these are all C2 lines, emission lines. And they follow this H2 region pretty well, this ionized region. And let's zoom in. And lo and behold, look, every one of those is a little squiggly C2 line. And this is really not noise. This is the shape of the line. And so from the shapes of these lines, we're talking about line profile functions in 300B, and I'm trying to instill to the students, this is important stuff. Because by looking at the line shape, you can discern the underlying dynamics of the regions you're looking at.
Can you explain what's going on with this plot? Is it like their spectra spatially?
Yeah,
on the
thank you.
y-axis? Okay.
Yeah, it's a raster scan.
Okay.
So every little postage stamp spectrum is looking through a different line of sight in right ascension declination on the sky.
Okay.
It's exactly right. So you're making a two-dimensional plot of the C2 emission across the sky. And you can see there, it's everywhere. Even way the hell off, you can still see little C2 lines. And so here's like a zoom in on one of them. So these are velocity resolved. So every spectrum we took had 1,000 simultaneously read frequency points. If you do radio astronomy, you realize spectrometers typically have what we call them channels. And each channel is a little piece of velocity. And for us, the spectral resolution was 1 or 2 kilometers per second per channel. So as we step across, we have 1,000 independent velocity measurements or frequency measurements of this line. And in this one spectral mosaic, there's 7,225 spectra, each of them with 1,000 simultaneously measured frequency points. So there's a ton of measurements to go into this map. And each spectrum was only took 0.3 seconds of integration time, which is pretty good for a Terahertz observatory. Okay, so since we got all these spectra and stuff, we can make movies because we have velocities and all that stuff. So here's the two-dimensional map. Okay, we're looking at, this is what we call in radio astronomy a channel map, which means we're stepping through the spectral line. And so here we go. So we go from high velocity through line center to lower velocity. Okay, so you can see in the line center, you get that butterfly effect in terms of line profile. So, well, that's all cool, but not that impressive. But what you can do is say, well, let's assume that there's a velocity gradient in this structure, in this cloud. So actually the velocity encodes the spatial distance along the line of sight. And this source is like that. So if you do that, you can make a much more fun map. Okay, here is the integrated intensity. And here's the little butterfly wings that I showed earlier. It's just C2 now. And this was a pretty dirty map. This is without any real smoothing. It's just as it was. No cosmetics to clean it up. This is an early map. And this is about a half a degree on the side. And now we can, since we have velocity encode the distance through the cloud, we can actually get a three-dimensional image of it. So it has a velocity gradient. And we get a three-dimensional point cloud, which means we can look at it from like any point you want, either like from us, from above, from the side, from the back, and you get an idea of the power of this thing. And this is only quarter of a square degree, and we have 62 square degrees. I'll show you another one here. So this is the NGC 333.6. This is going to be another map of made. It's actually Craig made this map, and he did it at the AAS meeting before his talk. It's like the day before. I don't know whether Craig's listening. Probably not. He's too busy doing things. So anyway, Craig made this. So this is of this little tiny region right here. And so what's going to happen is I'm going to run this. So this is what it looks like. This is C2 emission. It's not dust. It's not IRS. It's what we measured with Gusto. You can see the galactic plane there. You can see stuff above and below it. It's pretty cool. But the coolest thing is when you rotate it, because we know the rotation curve through the galaxy, which I was harping on earlier. So we can actually get a three-dimensional picture of what's going on here. And so here we are. Now, what's cool about these are other spiral arms. So we're looking at different spiral arms along the line of sight through the galaxy, because we know the frequency separation, the velocity separation, we know the rotation curve, so we can do that. So we can do that for the entire galaxy, the part that we were able to get from Gusto, given this sensitivity and spectral resolution that we had. We also have nitrogen-2 data as well. It's 10 times weaker than the nitrogen-2 line, but it's still there. It's going to take a while to pull it out of the data. And so we got to +2 or so degrees, and then we had to stop. Why did we have to stop? Because I can never get tired of that. Oh, before I tell that story, we also looked at the Large Magellanic Cloud. So here's the first spectrum we took toward the Large Magellanic Cloud at C2. Again, I just drew a line. I didn't take out the baseline again. It's really like here. So you can see the ionized carbon line peaks up very nicely. This was toward 30 Doradus, which is the highest mass star formation, brightest star formation region, like a whole star burst in the LMC. So we were able to measure this chunk of it. So all very new. Okay. So we launched here from McMurdo, as you saw. There's an anticyclone that sets up during the summer months down there, the winter months here. The South Pole is right there. I have other talks for times at the South Pole, but not today. But that's where the South Pole is. So this Earth is rotating, and that's why it makes these concentric rings. So each pass has a different color. So blue is the first pass, and then they change it to green, and then it goes to red. And we're taking data, and then it kind of stalls out here. And what happens is that the only day it turned out that we could launch, thank God we were ready, was December 31st. That's when the stratospheric winds had been set up for weeks, but on that day is when the surface winds also were calm enough for us to launch. That's pretty late in the season. So by the time we're getting here, it's getting toward like now, very late February. And then it's starting to get into spring and summer. And during the summer months, down there, the cyclone blows in the clockwise direction. So this is called turnaround. And so the winds, it kind of stopped, it pedaled, just sort of softly pedaled like on an exercise bike for days and days. And then the wind started pushing it back in the other direction around the continent. The other thing that happens toward this time of year is night starts to happen in Antarctica. When we're down there, October to January, it's light all the time. But now the night falls. And when the night comes, the balloon sinks. The air gets colder, the balloon gets colder on the inside. BV is equal to nRT, and the balloon drops. And the longer the night, the colder it gets, the more it drops. And so it was starting to oscillate in altitude. And every time you do that, it puts a lot of stress and strain on the balloon. And also you get lower and lower and lower as the night gets longer and longer. So by the end here, we're dropping like 40,000 feet a night. And then it was like a horror movie, waiting for the sun to come up and the vampires to go away. And then the sun would come up, and then the atmosphere would heat up, and the balloon would rise. And it's like, thank God, we can take data again. Also, when it got really low, it got colder because the atmosphere is thicker. It gets colder, kind of counterintuitively, and our cooling loop would freeze. And so we'd have to wait for the sun to come up, the balloon to rise, and thaw out the cooling loop so we could cook all our equipment. More than you wanted to know, but it was something. So it was the longest balloon flight of this type. 57 days, 7 hours. Now, balloon came down and finally reached the point where the balloon popped, probably either due to stresses, and also we started to pick up wind gusts at these low altitudes. So some combination of stress and strain, and the balloon gave up the ghost and it came down. And it parachuted down kind of unexpectedly. It actually landed far from here, about 40 kilometers away, but the parachute didn't disconnect from the gondola like it should. So it just parasailed across the ice from 40 kilometers until it plowed itself in deep enough that it goes no further. So this little pink blotch over here, this is a satellite image from orbit. And that's the parachute, and the gondola is over here. Is enough of it still there that it can cast a shadow? That's all we really know. As of this morning, there are some emails going back and forth. It looks like they're trying to have a campaign to go get the gondola next year in 26 to pick it up. NASA is obliged to go pick these payloads up and not pollute the Antarctic continent, if at all possible. We'd like to get the payload back because obviously we still have half the galaxy to do, so we want to do a Gusto too. All right. Okay. So what's happening with all this data? We have it. It's making its way through the data pipeline. We expect to release the first data release one, that's what DR1 is, to the public just in a month. We're supposed to have this done. And it will be also at that time submitted to IPAC. So it'll show up ultimately at IPAC like all the other far infrared missions. You'll be able to get it. Before IPAC puts it out, they take a while to churn it themselves. We'll post the data on Harvard Dataverse and here at the U of A, so people can access it right away by the end of March. So I hope everyone can use this data. There's no proprietary period. It's your data as much as it is ours. So we did get sneak peeks of it in order to figure out how to reduce it and make the pipeline do reasonable, helpful things. Other than that, it's up for grabs. So we're pretty excited about that. So that's the end of the Gusto part. While I stop and see whether there are questions. Yes.
So why the gondola was not retrieved immediately when it fell down?
The reason why is that it's way over here. So we were over here. That's McMurdo base is like right there. And then we take a little van out every day to the Ross Ice Shelf where the hangar was. But it's in the no man's land. There are Australian and Chinese bases, see, on the ocean side and here. And so it's a big family on the ice. People tend not to worry about national things very much. It's really, really true. And so NASA's already contacted the Australians. And I just learned today that they did go fly over the terrain and found that it's possible to get there. Because sometimes it's just like a boulder field of ice. You look at this. They said, no, it looks like you could recover it. So based upon that, there'll likely be an Australian US team will go from their base here on the coast inland to retrieve the payload.
Yes.
Yeah, I was curious if the coverage also covered Gould's belt clouds are relatively nearby. It looked like it stuck pretty close to the plane, but was there anything like in row O for Lupus and things that were a little bit out of the plane? Was that covered at all?
No, not really. We stuck to the plane. We didn't get to, well, we did have we had the targeted deep sky survey part, but we didn't get to it because the balloon, we launched so late in the year, we didn't have as much time as we wanted. We were hoping to have 75 days, but it ended up being 57 days. And so we actually had about 10 to 14 days left of cryogens on board. So we could have kept going and observed more, but we didn't get to do all those things. Yes. We'll have to do that on Gusto too.
It's an incredible data set.
Yeah, well, hopefully. But just, hopefully it's a legacy kind of thing. It'll just be there. My goal is, if guys who've been in my office is want to have like our Galactic, we have a Galactic plane survey a little bit from SuperCam. Remember SuperCam? We still have that. And then also we have the C2 and N2 Galactic plane survey from Gusto. But when we think about C2 and N2, we always think about these COBE maps from the FIRAS instrumental COBE. So we want to have the Gusto version of that, because ours has got thousands of times better spatial, 100 times better spatial, 1,000 times better spectral resolution. So that's what we're pushing for. Any other questions about Gusto? Yeah.
I was curious how far you can go. For instance, can you observe nearby galaxies or like local group galaxies?
You could, absolutely. Yes, you could. And they also do balloon flights from higher latitudes. Ultimately, we're limited when we're observing by the latitude we're at, which is pretty low, how far we can see north. And balloon drifts further north as time goes on. Also, we're limited by the balloon above us. We can only observe up to about 70 degrees elevation, 65 or 70, before the balloon starts to occult our beam. The balloon's huge. And you see it comes all the way down to the top of the gondola pretty much. But they do launch balloons from Wanaka, New Zealand. And my thinking for Gusto 2, we'll shoot from Wanaka, because then we can get the entire sky pretty much from that latitude. So that would be pretty exciting. And also you can go for a long time. One reason why Antarctica is really good is because the sun's up all the time to provide power for our hungry payload. Also, a nice thing about it is that there's no countries to fly over, which you have to get overflight from. They also launch balloons from Sweden, Kiruna, Sweden. However, there are some people who don't want us to fly over their countries. So we can only go as far. You launch from there, it goes to Canada, thank you very much. And we pick them up there after about 5 days. But you go much further, then you end up going over the Pacific and then over Russia, which is a no-fly zone. So that truncates the length of the missions. We can, a friendly Antarctica and the South Seas, we can keep going and going and going.
Oh, I was gonna ask a different question, but now I'm curious, like, is there any steering then? Based on what you just said?
No, we cannot
Right.
steer the balloon.
Right, okay, that's what I
We can
figured.
steer the telescope, 360, plus or minus 90, plus 90, 0 to 90. But no, we can't steer the balloon.
So if you were headed towards Russia, you would have to just like bring it down to the
Bring
ground?
it down.
Okay.
And there is a terminate command. We didn't have to use it. The universe decided to just terminate our mission. But no, yes, there is a terminate command where it basically pulls a ripcord through the balloon, tears a hole in it, and bring it down. And they typically do that on like US continental type missions, like from Palestine, Texas, to Fort Sumner. You can only go for a few hours or maybe 10 hours if you're lucky before you'll end up going over like Albuquerque or something. And they have to bring the balloon down sooner. So that's why Antarctica is sort of the premier site. Everyone's lined up to launch balloons from Antarctica because you can get the longest durations from there.
I was gonna ask before, and maybe this is obvious to the astrophysicists, but what would the difference between the N2 and C2 possibly tell
Oh
you?
yeah, absolutely. Yeah, so like I mentioned earlier, the C2 it can light up everywhere because it has its ionization potential is below 13.6 eV, which is that of hydrogen. Nitrogen has ionization potential, I can't remember table 2. But anyway, it's like 14 point something eV. So nitrogen 2 will only light up right next to a high mass star. Because if it goes trying to light up any further, there's no ultra high ionization potential photon, UV photons. They're all sucked up by the omnipresent hydrogen atoms. So nitrogen 2 shows up only in high mass star forming regions, whereas C2 will show up everywhere. So by blinking the two maps, you can get the difference between high mass or star forming regions versus just standard ISO. So they're a good contrast. Yeah, you bet. Okay. All right, what's next? Okay, time doesn't stand still. So there's been many ISM missions over the years to understand the life cycle of ISM, and Gusto is just the last one of these. STO 1 and 2, we had that. There was the Sophia, which is now down at Davis-Monthan. It's been mothballed. There was Herschel, which did tremendous work. Spitzer, which the U of A was a big part of. The MIPS instrument on Spitzer was made here. Japanese missions, an old heterodyne mission from Gary Melnick at Harvard Smithsonian, all the way back to IRAS. But what's next beyond Gusto? Well, there's Prima, which we got into phase A, which I'll probably say the PI of Prima is a former grad student of mine, Jason Glenn. I still had his old computer in my office, but if anyone wants to sneak in like that. So that's Jason's Prima mission 2031. And there's also other ones. There's other balloon missions in between, because 2031 is a long way, particularly for me. It's a long way, 2031. So what can you do? Well, there's balloon missions, as we've shown and others have shown. There's an Astros mission, which is a 2-meter telescope from JPL, which does a lot of the STO type Gusto science, but for more targeted regions because it's a bigger telescope, smaller beam. There's a TIM mission, Terahertz intensity mapper, looking at unresolved C2 lines and other things. And there's POEM, which is a new mission that will look at HD lines with a low resolution spatial resolution, fairly high spectral, but low spatial. All these things are all 2 meters, including Prima. So we need to break that blockade at 2 meters in terms of realizing large apertures. I tried and failed with Saltus, but there's still a lot of things we need to do for which we need high angle resolution. It's necessary for understanding the formation, migration, and mass distribution of exoplanets and protoplanetary disks, determining the properties of exoplanet atmospheres, determining the frequency of Earth-like planets, understanding the role of star formation. It goes on and on and on. And perhaps one of the most important things is breaking the far infrared confusion limit in extragalactic observations that plague smaller apertures. So this is something that Prima cannot do, even though it's mostly an extragalactic telescope. You really need a larger telescope for that. So what are we going to do in the meantime? Well, the next probe call won't be until 2030 something. So what can we do between now and then? So we'd like to try to fly a larger aperture, but very focused, doing heterodyne HD work toward protoplanetary disks. It's called the Terahertz orbiting Pioneer. NASA has low-cost Pioneer missions they offer each year or every other year for doing very focused investigations that include new technologies. In fact, instead of like a normal explorer type mission, like Prima in particular, where they frown on anything new because they don't want to take any risks, they're much more willing to spend a little bit of money and try to do some really interesting science at higher risk. So we're going to try to prove out this inflatable reflector technology for them. It's been around a long time, actually. There is a 14-meter inflatable parabolic reflector that went up at microwave frequencies way back in 1995. So this is a brand new idea. And since then, there's been a whole bunch of advancements in adaptive optics and all this. And we've had grants from various government organizations for 10 years pushing this technology. In fact, we've shown that it works even to the threshold of optical. We've used adaptive optics and optical to improve the performance of these inflatable mirrors. It's mostly getting a space demonstration that you really need to beyond what was done here. And also, this is a pretty large aperture. Can you really do? Well, this is 14 meters. One of the more recent ones is something my wife's probably watching. She's not going to like this. This is the Blue Walker 3 satellite. No relation, by the way. It has to do with it walking across the sky, I think, is what I read. But it's 8 meters on a side, which it shows what's possible from what you can deploy from a small sat. And speaking of small sats, we have another one called CatSat, which we just launched. It was launched on July 3rd of this past year. And this was all built here at the U of A. It's a student project. In fact, we had the original design meetings were around this very table some years ago now. It has an inflatable aperture. It's just only half a meter in size, but it comes from a 6U CubeSat. And it's happily orbiting us right now at 500 kilometers, doing its thing. We're going to actually deploy this guy next month because we've done everything else. Then we'll save this for last because it's kind of like a balloon, like in the old 2010 movie a long time ago. Once you inflate this thing, it produces drag, which will slow it down and it'll make it decay probably within 6 months. So we want to get everything else done. Meanwhile, it's taking lots of pictures and trying to do observations of the ionosphere and things like that. This won't be an issue for the top mission because we'd have a test-like orbit, which puts it far away from Earth most all the time. So it won't encroach upon doing ground-based observations from the Earth. So it'll swing around in a 13, 14-day orbit around the Earth. It's got orbital resonance with the Moon. So we would downlink the data on close approach to the Earth. Probably what we'll do is flip the sky around and use this as a big telecom antenna, which we can do. Right, just some of the optics pictures. So what we're going to try to do with this, and I should point out Camber Schwartz, who has U of A heritage here. She's the project scientist for this mission. And the main thing we're looking at are the HD lines toward the brightest protoplanetary disk. We have a top 10 list. You can probably guess who's on that list. And so what we do is we have a super duper heterodyne spectral resolution, so we can get like 10 to 6 resolving power. So we can get down to kilometers per second type velocity resolution of the disks. And since the disks can Keplerian rotation, the inner parts moving faster than the outer parts, so you can the habitable zones are like over here. This is getting toward the outer part of the solar systems, planetary systems. So we'll be able to do the mass profile through the whole thing. We'll also be able to do water lines. The brightest water lines in the far infrared we'll also be able to get on this little mission. So we're hoping that the data set from the top mission would serve as sort of a Rosetta Stone for understanding the mass of water distributions in protoplanetary disks. And here's like the mission schedule. So we hope to launch it toward the end of 29. Be the goal. Then what about having larger apertures than that even? What can we do? Are we just kind of out of luck? Can't get above 10 meters. Well, there's Saltus, right? I mentioned earlier, it's 14 meters. But NASA pretty much thought that, well, this is all great, but we want you to do a space demonstration of this first, more or less. So that's why we're doing the Pioneer. One reason to prove out this technology. So that's possible. But again, this would be like another probe mission, and that won't happen again, for another decade. There are European versions of interferometers in space, which also are a way of getting large apertures, which translate to higher angle resolution. There's the old U.S. terrestrial planet finder, Star One Spice, which is also a U.S. one led by Dave Leitsowitz, a concept at Goddard, and others. But again, the risk of flying a complicated interferometer scares away lots of NASA and ESA typically. So what can we do? Are we just stuck forever? Well, where else can we go? Where can we go? Back to Antarctica, of course, because there's Dome A in Antarctica. Here's where we were, McMurdo, where we launched the balloons, South Pole Base, old stomping grounds. Also, one of our team's old stomping grounds is Dome A. It's the highest point on the Antarctic plateau, kind of like Mauna Kea, but in Antarctica. So it's also the coldest, driest place on Earth. And it's water vapor in the Earth's atmosphere that sucks up our photons. Ice doesn't bother us. So we understood this for a long time. We proposed way back 15 years ago or so to the NSF to go to Dome A and put an observatory there. Initially, they said, well, actually, can you believe this? They said, go work with the Chinese because the Chinese are going to Dome A. So we had a couple trips to Nanjing Observatory in Beijing, astronomy departments, and we did have a collaborative trip to Dome A where they took a site. They took a site testing instrument for us called preheat. Heat was high elevation Antarctic Terahertz telescope, and they proved that the nice site really was dry. The NSF did fund us to put a little observatory on Dome A. Not right at Dome A, was like some 60 kilometers, I think, from the Chinese base, which Craig Kalesa found out to be from satellite observations, found out to be a better location anyway. And we set this thing up. And actually, here's a picture of Craig on Dome A with this instrument. And if this is a weird looking siderostat type of deal, where the light comes in, hits this flat piece of aluminum, comes over here to a standing parabola. And then this has to do with the fact that I was a grad student for John Krause at Ohio State. The bigger telescope was like this. That's where the idea came from. So we would observe the sky and tilt it in elevation and make a big map. So that worked out great. Since then, though, we focused on Gusto. And so we stopped going to Dome A to get Gusto done. But now our eyes are turned back to Dome A. In the meantime, our Chinese colleagues actually put an FTS down there and got the atmospheric transmission at Dome A. This is in terahertz. That's like 100 microns right there, wavelength. And just so you can better understand, this is the wavelength coverage of James Webb. This is a transmission from Dome A. Holy cow, look, you could do a lot. So transmission is almost perfect over many of these wavelength ranges. So you could do a lot of follow-up science down there and build whatever size telescope you want that logistics will allow.
It's 1250.
Okay, I'm on 1248, it says right there. I'm going by the ring clock. Okay, so anyhow, so you can do it. So why did they even bother with James Webb? The reason why is because even if I don't think they knew about this, to be honest, but one way they can still justify doing it is that in space you can radiatively cool the aperture down to very low temperatures, like 55 Kelvin, so you don't swamp your detectors, which makes the James Webb Space Telescope 20 times more sensitive than a comparable telescope down here. Okay, but still, I don't know, you still do a lot of stuff.
Isn't 55K about what Dome A is?
It gets pretty cold. It's like 100 below. So what could you do? Well, you can put an interferometer on Dome A and piece together a larger telescope. is the idea going forward. So we actually have a proposal in right now to NSF, who knows what will happen, to establish an NSF Science and Technology Center here at the U of A called CAST, which includes astrophysics to go look at putting an interferometer on dome A, among other things. It also includes using VR and AR solutions to increase the ability to actually use Antarctica, and more people can be involved remotely because it is hard to get there. STEM education, farming in Antarctica, sustainable life support systems. Little is known that the U of A actually built greenhouses that are in use right now at the South Pole Station, McMurdo Station. And also using Antarctica as a surrogate for understanding life on icy worlds, for instance. So a lot of people from LPL involved in this effort. So we're waiting to see what happens with that. It was a pre-proposal we put in November. We're waiting to hear back. And I will stop there because Allison knows I have to go teach.
Awesome.
And Q&A, we thank our speaker again. See you next week.
Yes,
Thank you so
guys.
much.
What a nice. Thank you.
That was very top of this.